Alright, silly people, here's the situation. We're going to be proving a few relations that Griffiths has given us in the chapter. Uh, and one of those, to start with, is going to be that the transpose of two matrices multiplied together um, gives you the transpose of the second times the transpose of the first. Um, and this is going to be a little bit involved, but you go back to the definition of two matrices multiplied together. I think Griffiths calls it U sub ik, but we're going to call it S times T sub ik because it means the same thing. Um, and then the definition is that it's the sum of J of Sij times Tjk, right? And then we're going to take the transpose of both sides. So on the left-hand side, the transpose is going to be pretty obvious. On the right-hand side, not so much, because as of right now, Sij and Tjk, with them being in the sum, are both scalar quantities, and so their transpose don't really exist. But we know that when we take the transpose of a thing that is indexed, that you just flip the indexes. So we know that this is going to be the STKI instead. So on the right-hand side, to reflect this, we're just going to put a K every time we see an I, and put an I every time we see a K. And you get that sort of thing there. Right? But now you can be like, okay, Skj, if we were treating it as a matrix, would just be the transpose of Sjk, and Tji would just be the transpose of Tij, right? And then you reorder it. You don't have to, but I did. You reorder it so it looks more like the multiplication formula. All the indices are in the same order as before. So then you know that ST transpose is going to just be T transpose times S transpose. And that's pretty funny. So that's cool. The next one is that he wants us to prove that the Hermitian conjugate is the same sort of deal. So if you take the Hermitian conjugate of St, you get the Hermitian conjugate of T times the Hermitian conjugate of S. This isn't as subtle because we know that the Hermitian conjugate is just the transpose, and then you take the complex conjugate of the transpose, so it's going to be like T tilde S tilde, but then you take the complex conjugate of the whole thing. But then the complex conjugate is distributive multiplicatively. So you have T transpose complex conjugate times S transpose complex conjugate. So you just have T dagger S dagger. So that is proved. The next thing that he wants us to prove is that if you take the inverse of S times T, you again get like this reverse order T inverse S inverse. The way I did this is I just took ST and multiplied it by what would be T inverse S inverse if this were the case, and checked that it is equal to 1, which it is because T times T inverse is 1, so now this is S inverse, which is 1. So, yeah, this is a true fact. Then he's going to ask us, is the product of two unitary matrices unitary? Unitary matrices have the quality of a dagger equals a inverse, right? That's the definition of a unitary matrix. So what I'm going to do is I'm going to say AB and multiply it by its dagger, so it's a Hermitian conjugate AB dagger, and check that is equal to 1. Um, and so we know that the Hermitian conjugate of a product of two matrices is going to be the Hermitian conjugate of the second times the Hermitian conjugate of the first. But then, since they're unitary, these are going to be equivalents to inverses. And then B times B inverse is 1. And then A times A inverse is 1. So this does work. So this does work. And so, yeah, AB dagger is equal to AB inverse. That is true. The next thing that Griffiths has us do is multiply two Hermitian matrices together. And the thing is to check if it's still Hermitian. And the quality that Hermitian matrices have is that they are equal to their own Hermitian conjugate. So we're just going to check this. But we know that the Hermitian conjugate of CD is just going to be it's going to be D dagger, C dagger, right? So that has to be equal to CD, but we also know that these are both Hermitian matrices, so this is just DC equals CD. So if we rearrange this, so we got CD minus DC equals 0. That is actually just the commutator of C and D. So the only scenario in where the product of two Hermitian matrices is still Hermitian is if the matrices commute. Next is the sum of two unitary matrices, still a unitary matrix. So that is just saying if you add a unitary matrix E plus a unitary matrix F, is it still equal to, is the Hermitian conjugate, I should say, still equal to the inverse? So what we're going to do is we're going to multiply E plus F, the unitary matrices, times the Hermitian conjugate, and see if it equals to 1. If so, then the sum of the two will be unitary. So we've got E plus F times E dagger plus F dagger. Then you can distribute those. So you have E dagger plus E F dagger plus F E dagger plus F dagger. We know that the E and F are both unitary, so the Hermitian conjugates are equal to their inverses. So we got Fe inverse plus F inverse. And then so that is 1. This is the same. This is the same. Plus 1. So it's not equal to 1. It's in fact equal to something entirely different, which is a little bit hard to predict. But suffice it to say, it's not equal to 1. So therefore, the sum of the two unitary matrices are not unitary. The next thing that he's going to ask is if you add together two Hermitian matrices, do you still get a Hermitian matrix? So we're checking that if we add together G plus H, assuming they're both Hermitian matrices, and take the Hermitian conjugate, do we get G plus H back out? So the way to check this is to just distribute the Hermitian conjugate to G and H. So we get G dagger plus H dagger. And so, yeah, these are both Hermitian matrices, so this is just G plus H. So, yeah, it's still Hermitian. Cool.